it's a guide to Earth electrode systems. It's not, we're not going to go into any great depth because we would be here for a hell of a long time. So that's me, Simon Sorsby. I'm a chartered engineer with the IET. I'm design manager with Wallis. Wallis, just a quick overview. We were founded in 1946 in Nottingham, originally making non-ferrous marine castings, propellers, gearboxes, etc. Now we're a design, manufacture and supply of earthing, lightning protection and surge protection systems components, selling worldwide, about £30 million turnover, 50% of that in the UK, 50% of that overseas. I'm literally going to spin through these because this is, I'll say, it's not what you're here for. You need to know the good bits. Other services, surge. There we go. Right, so I originally trained with the MOD, systems engineer for BAE Systems. I worked on the oil and gas in Libya, Iran, places like that, looking after different bits and bobs. I worked for, I'm sure many of you have got Omega Red Group in the dim and distant past. I was design engineer for those guys and then contracts manager. I then moved over to be primary system designer for Western Power Distribution before a short time at Energetics, before joining Wallis 4 and a bit years ago. I'm also sitting on the 50522 committee. Power earthing above 1 kV, that is the standard that you need to have in your hand. Right, so we're going to run through these things again very quickly. Very much the same as lightning protection. Power earthing should be the same. So, Sod's Law, you know, it's one of these things. We'll cover it off, but never approach lightning protection systems or power earthing during the risk of lightning. Reason being, you get a strike of there, it's going to come up with the power system, and it will find its way through to Earth to a greater or lesser extent. And again, same with the switching event. That is when the fault is most likely to take place. Commissioning, decommissioning, switching events. That's when you likely get a fault to Earth, so don't go near it then. And yeah, biggest problem we have at the moment, HSG 47 tells us never break ground until you're clear of the, sorry, put your teeth in, until you're sure the area is clear of buried services. Right, that is a big one. That is one we really want to get across. Earthing systems are not inert. In certain circumstances, it's dangerous to live conductor. We've been to many sites recently, hospitals, data centres, places where there's a lot of electronics, a lot of drive motors, things like that. Put a clamp meter around the earth, and we've had in the region of 20 to 30 amps flowing down under steady state conditions. So if you go and disconnect that earth with one of these magic disconnect links that everybody likes, and you're bridging across that, it only takes, what was it, 20, 30 milliamps to put the heart into fibrillation, and you've got 30 odd amps going through there. Green and yellow cables are not dead. There you go, and that comes straight out of BS743 over the code of practice for earthing. An earthing system should be treated as you would any other part of the electrical system. Right, so applicable standards. Again, you guys will know most of those. LV is one thing, HV is more. There are a lot of standards covering HV, let's put it that way. There are the British standards, there are IEC standards, there's EN standards. You then get into the Energy Networks Association standards, which is the umbrella body for Western Power, UK Power Networks, Northern Power Grid. So you might have to work to these. And then you also have the DNO standards to work to as well, depending on where your system is connecting into the existing network. So, and it's not as simple as they all tally together. They all tell you something slightly different. So you have to work to the most onerous standard. Again, sometimes you may come across these. There's some good information in them, but not something you probably see in the UK. That is a little flow chart of the process we use when we're going out doing these soil electrode system design. You need to know a lot of information before you start doing your designs. You need to know fault clearance time, fault levels, geology of the ground, where the earth system's going, and a lot of other stuff besides. So that is just a quick sort of précis of where we go through with a retaining site. Each and every time you are putting an earth electrode system in the ground, you should really be doing a soil resistivity survey. The reason I say that, we might think the geology is the same across the city, same across the general area, but it will change. And it might change significantly, and enough to throw your readings off. So it is good practice to do a soil resistivity survey each and every time. From there, that is your base information. If you get that data wrong, then everything else is going to be wrong as well. So you need to get that right to start with. I'll flip onto this on my apologies. This is going to flip backwards and forwards slightly, but I'll go into CDEG's software in a little while. But we then process the data using the CDEG software. You can do it paper and pen method. You can do uniform models using paper and pen. We find this gives us a nice multi-layer model, and it is accepted by the DNOs, National Grid, and a lot of big companies now. It is becoming the UK standard. You need to compare, again, the soil resistivity survey is only as good as the measurements you're gaining. If they're being fouled by something, buried services, overhead lines that are inducting stray currents onto your test leads, it will affect the readings. So if you've got a geology map, it's always good practice to have a look at the geology map, compare it to the tables in the British Standard, because they give you some probable values for different geologies, and then compare it to your readings as well. At least it's a three-way check then. You then need to collate, as I say, your electrical data, your three-phase symmetrical fault currents. Again, I'll come on to that and the reason we need that. Single phase to earth durations, etc. You also need to determine whether it's underground fed or overhead line fed. The reason behind that is, if you've got an overhead line fed standard wood pole 3-wire construction, it is literally 3 wires. There is no earth wire, there is no neutral wire, there's no return. So all of the earth fault that you have at your substation will go into your earth electrode system. Whereas if you've got a cable connected system, and I'm talking like 100% cable connected now, you will have the cable sheath or the armour or whatever connecting your site back to the source. So a percentage of any fault will go back up that path as well. So you have to do the fault current split. So we then build all that up into the CDEG's model. We actually draw all the conductors onto the software itself. We put the soil model in. We tell it what fault level it's going to be at that specific site, and it analyses. It analyses the site, then it analyses the earth electrode system, and it tells us what the touch, step, and transfer touch, step, and rise of earth potential limits are going to, or values are going to be. We then, as engineers, need to be able to sort of recognise whether they are within permissible limits or outside permissible limits. And that, again, those permissible limits are going to be down to ground coverings, clearance times, etc. But again, I'll touch on that more in the floor. The magic less than 1 ohm theory. Now, this was one of the things that gets pulled up time and time again. DNOs used to stipulate this. A lot of the big consultancies still stipulate this. The less than 1 ohm value is it might be right, it might be wrong. But what makes 1 ohm correct and 1.1 ohm incorrect? It's the fact that you need to make the site safe and suitable. So the driving factor's got to be, is the site safe and suitable? Not what the resistance value is, because it's all going to be down to your fault currents coming into the site. It's going to be down to the resistivity of the ground. It's going to be down to the clearance times. So whether 1 ohm is right, wrong, or indifferent it's one of those. I mean, we can go to a site, and if it's got a high fault level with a slow clearance time, we might need to get the earth electrode system down to 0.1 of an ohm. If it's the other way, and you've got quite a low fault level, then you can get away with 5 ohms or 6 ohms, depending on what the configuration of the network is. So it's not as easy as just saying, put a less than 1 ohm earth rod in, you're good to go, everybody's safe. Yeah, it sort of comes from the fact that historically lead sheath cables, the centre of Birmingham, the centre of Nottingham, centre of Leicester, all these big cities, all of the distribution network was connected together with these conductive sheath cables. So you had this wonderful global earthing system. You only needed to really get a reasonable figure at your substation, because you know full well that all of the fault level was going to go up the cable sheets into the general mass of Earth that way. Well, unfortunately, they've ripped all these lovely lead sheath cables out and put triplex in everywhere, or EPR cable, I think that Western Power use now. So you've lost all that global earthing system. Fault currents are tending to be higher. Low loss transformers, the DNOs are putting in low loss transformers. Where there's heat, there's losses. So they're putting the low loss transformers in. Problem with that is they are lower impedance, historically. If they're lower impedance, then you tend to get higher fault currents. If they're higher fault currents, it causes me, as an earthing engineer, quite a few problems. So this is, and forgive me again, but that summed it up. This is the extract from ENATS 4124. This has been completely rewritten and was reissued in November last year. This is almost the Bible. It is, I've got to be honest, a lot better document than BSEM 50522. If you can get your hands on a copy of this, there's a lot of good examples in here, but a lot of good theory and a lot of good maths in here as well. So, but this is actually saying, the cables provide a degree of potential gradient, thus reducing, as well as, I think, there you go. Experience has shown that this approach is no longer applicable, particularly given the now widespread use of insulated sheath cables. So it's there, it's documented. ENATS 4124 says that this approach is no longer applicable. So when you're coming across this less than 1 ohm earth, it's got to sort of start you thinking a little bit. Right, forgive me. So, as I say, it was bouncing around a little bit. Soil resistivity, let me teeth here, is a measure of how much the soil resists the flow of ground. So again, the different geologies across the country, across the county, across the planet, will resist the flow of electricity to a greater or lesser extent. You need to know what that is before you can start putting your earth rods in the ground, your tape in the ground. All the earth rods are, all the tape is a means to an end. It's a means of connecting your high voltage earth, your LV system, to the general mass of earth. We could get a wire and just go like that, we would be, it's dead easy. But it's just a means to an end. So we need to know how many earth rods are going to go into the ground to give us a required value, not less than 1 ohm. Measure ohms per meter, varies with local geology. We tend to use the Venn method. There are other methods out there. Schlumberger method, I think, yeah, I put on there. That tends to be the oil and gas. They're all sort of a similar principle, but the standards tend to work around the Venn method. As describes, the standard separation distances in 50522 as well. That is the standard layout for the Venn method. So if you're ever on a site and you've got some guys, be it us, be it one of our competitors, come out, that is what we're doing. We're sticking probes in the ground. Through the outer two probes, you're actually injecting a fixed current, milliamps, nothing great to it. And through the inner two probes, you're actually measuring the voltage. From that, you get very simple V equals IR, gives you the apparent resistance. You then do a little formula, the rho equals 2 times pi times A times R. So A is the different distance between the rods, R is the resistance from the meter, and then that gives you the actual resistivity of the ground at that depth. We vary the distance between these rods because Dr. Venner, I believe it was in 1890 something, I can't remember, but it was somewhere along those lines that he did all these experiments, and he found that electricity travels through the ground in a hemispherical pattern. So depending on how far apart your probes are, that's how far you're looking into the ground. So we will carry out a series of surveys, ranging from sort of half a metre apart right up to 100 metres apart, depending on your substation size. You take all those readings and you carry out 1 or 2 surveys around the site to actually give you as much data as you can to get to make sure all the data is coming together. Typical values yet out of 50522. Again, you can see that the variances are massive. I can sort of speak for Nottingham because that's where we're from. We've got a top layer of nice red clay where it's somewhere between 20 and 200 ohms per metre. But then down me, we've got sandstone at 2,000 to 3,000 ohms per metre. So it depends where you are in the city to what coverage you've got. I think it'll be very similar around here, the same right across the country. So for central London, where they've got metres and metres and metres of the lovely London clay, and you can just get half an ohm for knocking an earth rod in the ground. Fault level data. So this is what I was alluding to earlier. If a site is cable fed and the cable sheath or the arm is terminated onto your cable box of your transformer, your RMU, whatever, that is connected, and your body of your RMU is connected to Earth, you will get a percentage of the fault going to the general mass of Earth and a percentage going up the cable sheath. I think I have got a little sketch of that. We asked for the 3-phase symmetrical fulcrum when we're doing the designs because that's what we tend to size the conductor to. So to determine whether we're putting 25 by 3 copper in the ground or 50 by 6 or whatever, we tend to rate it to 3-phase symmetrical. And I have got a little drawing. And forgive my crude sketches, but what I'm trying to sort of say there is, and under IEC, like BSEN 60999-3, which talks about simultaneous but independent faults to Earth. So it's saying if you've got an RMU, for instance, and that faults phase 3 to Earth, and you've got a transformer that faults phase 1 to Earth, and it's sharing the same Earth system, as you do in a little distribution substation sometimes, you can actually get a phase-to-phase fault through the Earth system. So that would be the reason you would size the copper to the 3-phase symmetrical. UK standard, yeah, various data determine the conductor required. So we need to know what conductor material used. Predominantly in the UK, it is copper. We are coming across more and more sites that are being built by say German companies or something like that, where they are trying to bring in galvanised steel, and they're trying to use galvanised steel in the ground as the main earthing system. It's fine, as long as it's rated, as long as it's sized correctly, as long as it's jointed correctly, fantastic. It's just an absolute pig to work with. Starting temperature, you need to know the starting temperature. We tend to work to 30 degrees C. Again, worst case, UK summer, sitting in a switch room or something like that, we would hope it's going to be about 30 degrees C. Maximum allowable temperature wise. Now that can vary. I think 7430 talks about 250 degrees C, and that is where it's passing through concealed or confined areas, such as through wall spaces or somewhere like that. You've then got EN ATS 4124, which then talks about a maximum temperature rise of 400 degrees C, and that's for copper in the ground, an open gear substation. So you can push that copper very, very hard, but obviously then you've got to be aware of what is around that copper under fault conditions. You're then obviously going to know the fault current. The conductor jointing methodology will make a massive difference as well. Whether you're exothermically welding a joint, whether you're bolting a joint, whether you're clamping a joint, the hierarchy tends to be an unbroken piece of copper, a braze, an exothermic weld, a clamp joint, a bolted joint. And that tends to be where we will get to. That's not documented anywhere. That's just us as a manufacturer selling all these things. When we get in a type test, that tends to be how we see it come back. and fault duration, obviously, because the longer the fault duration, obviously, the bigger conductor you need. That is just a little takeoff, and forgive me, it was huge values because I did this for a customer out in the Middle East, but that just gives you some idea of for a 31.5 Ka fault current for a 3-second duration. Again, you tend to try and match the conductor size to the switchgear rating. So you might have 31.5 Ka here if you're right up the back end of a bulk supply point, or very close to so I know this side of the Midlands, you're 132 to 11 predominantly, whereas the East Midlands, we're 33 to 11 transformation. So you can get a lot higher fault levels on this side as well, so you just have to be a little bit careful. But as you can see, on a spur, so that's a single run of copper, you would be looking at 310 mil minimum. If you've got a parallel or a loop, then you can downrate it to 60%, and you're looking 186 mil. So it's still some quite decent sized copper. Yeah, I mean, again, this is the different standards give you different guidance. There's not a great deal mentioned in 50522 about how to connect equipment up, whereas TS 4124 actually gives you a little bit more guidance. It's a little bit more practical. It gives you a bit more help, and that does say, along with Western Power specs as well, they do say you should have 2 fully rated connections from the earth system to your HV plant. So if you do lose one, or somebody comes along trying to fill his Christmas box up with a bit of copper, then you've still got a secondary connection. And again, 60% of the rating where a conductor loop may be formed, or such as part of the main earth system. So when you've got a ring around the substation, you've got 2 diverse paths. Right. So system design, basics. Every time we design an earth electrode system to be solved the same way, we get the HV equipment, we put a ring around it, because at least by doing that, you are protecting somebody who's standing on the ground, touching the piece of equipment. You've equipotentialized the ground to the piece of equipment. So if that equipment goes live, you are actually limiting the potential difference, or the touch voltage as we call it, between you and the piece of equipment. Again, 2 fully rated connections to allow for redundancy. Determine what area is available for the earth electrode system. This is becoming more and more of a problem for us as designers, because you will have a big built-up city like Birmingham. You will want to put a new substation in somewhere, and you'll say, right, you've got that room there. Yeah, but that room's on the 3rd floor. Where am I going to put my earth in? Oh, well, there's a little bit of ground out there, and you go out and it's like 2 meters by 2 meters, and you think, yeah, great, thanks for that, thanks. There are ways and means to it, but you need to know up front. And unfortunately, historically, earthing has been one of those things that's been left to right to the last minute. And then you have to start getting drill rigs in and things like that, because if you don't go out, you've got to go down. If you sort of start to think about these things a little bit earlier on, sometimes you can, especially when a building is being cast or is coming out of the ground, you can start using piles. You can put earth rods through the slab and put earth rod seals on. You can do these many different ways of doing it, but it just needs a little bit of planning. If that ground floor has already been cast, then I'm afraid it's a little bit late, but that's one point. Copper bond and stainless steel rods are commonly used in the ground. Copper bond are the big ones. They're the ones you're going to see. Steel with a copper coating. We tend to design mainly for 4.8 metre rods. Now, I tend to use the analogy that if down in London you need to get an earth rod in, and you've got a big bloke with a Kango, you will get an earth rod down to 12 or 15 metres, because it is London clay, and you will just knock them straight in. Whereas, again, Nottingham, you might be lucky to get half a metre in some places. So again, you need to know what the ground makeup is. Perimeter fences are a big thing. Again, sites are getting smaller. You know, perimeter fences can be a real area of contention, actually, because perimeter fences are normally on the perimeter of your site. If you will bond your perimeter fencing to your earth electrode system, you've then got to start taking account of people, the general public, walking up to that fence from the outside. And under fault conditions, if that fence is bonded to your HV earth, that fence is going to be at the same potential as the substation under fault. So you can have people walking up, grabbing the fence. The best way around that is to put a perimeter tape 1 metre off the fence line to equipotentialise the general mass of earth to the fence. But that's not your ground. You can't do that. So again, you've got to start looking at these things slightly differently. Yeah, the remaining area of the site, you use the site you have to the best ability. All extraneous metal work within the site can be equipotentially bonded. As per everything else that we do, be it LV earthing, be it equipotential bonding, you're dragging everything to the same potential. If everything's at the same potential, there's no potential difference, no current flow. Earth conductors be installed between 500 and 1,000 mil below finished ground level. The idea behind that is, down below sort of 300-ish mil, even with the worst winter in the UK, the ground should not freeze below 300-ish mil. If the ground freezes, the resistivity actually goes through the roof. The resistivity changes, frozen ground. So if you've designed something based on 100 ohms per meter resistivity, and you know the fault levels are, or the resistance is fine at that, and then the ground freezes, your earth system has actually lost all its performance. And the actual resistance to earth then could go up quite dramatically. So if that goes up, then your rise of earth potential could go up, your touch potentials could go up, your step potentials go up, and actually you could end up with it being an unsafe site just because the ground's frozen. So that's something else you've got to be a bit careful. This was a little site that we did. I'm sure you guys have come across all these stall sites that they're shoving in these short-term operating reserve, little gas-fired generator set sites that are being shoved in right up and down the country, because all the coal-fired generating stations are going offline. We need resilience as a country. So what they're doing is any old business units, any old industrial units they are finding, they are putting with a decent electricity connection and a decent gas connection, they will put a series of generator sets in, they will connect them up to the grid, and as soon as National Grid needs additional power, all they do is dial in, fire these things up, they're going in everywhere. This is just a little sort of representation of what we sort of did on the site. So it's a 33 kV connection, so it's coming in from the bulk supply point, it's only a couple of 100 meters away, 33 inches transform down to 11, and the actual generator sets would sit up here somewhere. We're actually outputting at 11 kV. There was a little HV to LV transformer just for auxiliary supplies in there. But as you can see, what we've actually done, we've split the site up, put tapes in. You can't really see the symbols very well, but they're the earth rods. And we've actually tried to surround all of the main pieces of the plant with copper where we can. Again, making best use of the ground we've got. You're surrounding the copper to equipotentialise the ground you're standing on, and yeah, it's just an easier way of connecting everything up. System design, yeah. So again, coming back onto this, percentage of the earth fault will flow to the earth system, percentage will go back by the cable sheath. I have indeed, and again, forgive my little sketches. I find them a damn sight easier to do this way and just demonstrate it than actually try to explain it sometimes. So as you can see, you've got the 33 to 11, and then your on-site 11 to 400 volt substation there. So this is what I'm sort of saying. You've got the cable sheath, you've got the sheath and the cable bonded to that substation there, solidly bonded to the primary. So any faults on there will actually go through the general mass of earth and at the cable sheath. I think the next one, there we go. Sorry, there we go. Through the general mass of earth and back at the cable sheath. So that's your fault pack. So again, it just shows that rather than looking at earth systems like that, your local substation, you have to look at the network as a whole. Because although you might have an earth system for that substation, and you might be putting earthing in there, you might have another substation here and another one and another one. They're all going to be linked. So you need to look at the network as a whole, if possible. A lot of the time you just can't get the information, so you have to do the best that you can, and unfortunately you do end up with an over-designed system to a certain extent, but better to be safe than sorry. Excuse me. Only a percentage of the earth fault will go to, yeah, we've said that, yeah. Percentage will travel via the source, cable, IGR required, yeah. So we need to know what current is going into the general mass of Earth via your Earth, because it's that that's going to dictate the rise of Earth potential. Rise of Earth potential rise, ground potential rise, all the same thing. Very simple Ohm's law. So V EPR equals V equals IR. That's it. So I being IGR, which is the current going into the ground, R being the resistance to your Earth system. Dead easy. I mean, the vast majority of anything we do on earthing is Ohm's law. It's just getting your head around the components. Fault clearance times, because again, the human body can withstand more current for a shorter duration time and less current for a longer duration time. Does that make sense? Right, so again, little sort of representation there. Standard towers that we have all across the UK, and then that top wire being the shield wire, being the earth wire, whatever you want to call it. But that means there is a connection from that tower to that tower to that tower to the substation, both ends, so everything's connected together. Whereas the nice wood pole system that we have around East Midlands, West Midlands, vast majority of the country, got 1, 2, 3 wires, no earth wire, no return wire. So everything that happens is going to be, all the fault is going to be going to the general mass of Earth via your Earth system that you're designing. So it needs to be, you need to know what's happening in the feeder network, if that makes sense. So there's a lot to it. As I say, CDEX, right. This is a Canadian piece of kit. It's very, very good. It is a very good piece. It's not particularly user-friendly or intuitive, but it is a very good piece of software that's been put together by scientists. I mean, these guys, we go over and do training courses with them. They come and do the courses here. They are very clever chaps, talking about algorithms and all this clever stuff, way beyond what I'm into, let's put it that way. It's a modular piece of software. You can buy or use whatever modules you want. It's bloody expensive. So to use more than, or to buy or to pay for more than what you actually require can be a little bit expensive. So we actually use these, and we find that in the UK, these are the modules that we use the most. So RESAP is the soil resistivity analysis software, and that's where we get the raw data from the field. We actually analyse it in RESAP, and it gives us that composite soil model then. We can then use either MOLT, which is a nice simple module, and that is very good for using, say, a GRP substation at the end of the road, very good for modelling that, and very good for modelling, say, if you've got a GRP enclosure substation and then got a metallic gas main running next to it. You can model the metallic gas main, and you can see what the transfer potentials are between the two. See if you're going to cause any problems to the gas distribution network. Then you've got moles, which is looking at, that tends to look at bigger earth electrode systems. I'm talking probably somewhere up in the region of 50 meters. According to the earth map to the other, it's 0 ohm impedance. Reality, even as good as pure copper is, you will still have impedance in the earth map. So actually moles does take that into account, and you can actually do multi-frequency analysis with that. So rather than just 50 hertz, if you've got some funny plant on there kicking out 400 hertz or military applications that run at 400 hertz, then you could use that to analyze it. My apologies. then there's the FC disc, which is a simplified fault current distribution analysis. Again, what you can do on that is you can put in your distribution substation, your feeder substation, your feeder cable parameters, your sheath impedances, mutual impedances, things like that, and it will give you an idea of the percentage split between the general mass of earth and the cable sheath. There are also some very, very good formulae in ENA TS4124 and S30, both very good documents that to do that longhand and with MathCAD or something like that is fairly straightforward actually. The reason we use CDEX, for as expensive as it is very good. It's accepted by National Grid. It's the only one that's accepted by Western Power. It's actually written into EE 89-2, I think it is. So if you do a substation that needs to be accepted by WPD and use somebody else's software, they'll throw it out. Again, I'm going to really scan through this. I realise time is creeping on. Earth potential rise, ground potential rise, rise of earth potential, all the same thing. It's the potential relative to a distant point on the earth. So I've got an 11 kV cable in my hand. I'm going to touch that to the earth system. That face to earth is going to be 6350. It is actually going to energise the ground we're standing on to 6,350 volts, working on a 0 ohm network. Between there and there, you will have a difference in potential because the ground is a resistor. So when there's resistance, this potential difference, so you might have 6,350 there, you might have 5,000 volts there. It's all down to the ground makeup again. Okay, that's a little output from CDEX, very simplified. So that there is a little square substation with an earth rod either end. We've injected, I think we've just injected 11,500 volts into that. But it actually shows you that as the fault current runs away from the site, trying to get back to the source substation, you are actually getting a potential difference across the ground, and you can see it's, it can be significant values. Okay, this is exaggerated slightly for the purposes of this, but there can be some quite big differences on the ground. Again, going back to that store site that we were looking at earlier, we've then got, because we've got the rebar in the slab itself, that's all connected in, so that's potentialised the ground there, but it's actually pulled it down to 160 volts, and actually, as you creep away from that, you can see between 160 volts there and creeping out to sort of 130 volts there. That's a brilliant site. That is, the ground resistivity was brilliant there. The bulk supply point was only just up the road, so it was fantastic because I would say probably 80% of the fault current went up the cable sheet. So actually the general mass of Earth saw very little fault current. If you're on the end of a very long cable feed, 2, 3, 4 kilometres of cable impedance, then you will get a hell of an amount of current going to the Earth system as opposed to what's going up the cable sheet, if that makes sense. Again, and forgive me, I could talk about this for quite some time as well. To combine or not, HV and LV earths. It is always better to segregate HV and LV earths. But there are very, very, very few installations today that you will find where you can actually do that. Especially when you're taking an HV substation, building it into a student accommodation block, office block, hospital, whatever. That hospital, that student accommodation will be an LV environment. You have the rebar bonded to the lightning protection system. The lightning protection system is bonded to the LV network as part of the 18th edition wiring regs. You have to do it. So by virtue of you then pulling that HV transformer reman unit into that LV environment, you don't have the isolation between the two. So if you don't have the isolation between the two, you've got to bond the two together for safety reasons. So therefore, you've got to take into account the rise of the potential. 50522 does talk about a stress voltage of 1200 volts. So you're not actually forcing more than 1200 volts up the LV of an office block or something like that. They're saying that laptops, lights, projectors, etc. should have a withstand of about somewhere between 1000 volts, 1500 volts. And so by the time you've got a bit of impedance on that, coming up the network, 1200 volts, rise of earth potential should be all right. And by bonding the two together at that, you should be okay. There are other instances where if you've got telecoms in the building, you might have to look at a lower value, because S34 then talks about 430 volts contours, because what the Open Reach, Virgin Media and people like that, where they're bringing copper pairs into your building, they don't want that sort of level getting onto their 50 volt telecom systems. So again, you're not just looking at one value, you've got to look at 1200 volts, 430 volts, different values. Yeah, that's all. That's the part past on that. Yeah, so what they were actually, what this is trying to demonstrate is that the 11 kV RMU close coupled substation, HV earth sitting around it, and then you've actually got your earth potential rise contours coming away. And to make that safe, you're actually trying to put the LV earth installation outside of that 1200 volt contour. Some of the standards, some of the old DNO standards give you a figure, and it says, shall be not less than 7 meters, shall be not less than 9 meters. Unfortunately, again, that is a little bit, we did a job up at one of the RAF bases in Lincolnshire. We ended up, because of the very long cable runs and the very small cables and very poor ground up there, we ended up having to have a 25 metre distance between the two systems, just because the rise of earth potential was high and the ground was poor. So it just goes to show that these standard values you get in a lot of these documents aren't always as good as they should be. Again, touch potentials, sorry, again, I'm flip-flopping around a little bit with this. Touch potentials, potential difference between the energized object, that, so it's a substation, and the general mass of earth that you're standing on a metre away. So it's that potential difference through the body into the ground, and it's that loop. Very much as that little chap standing there. That's just an extract from 50522, so it's actually showing you there permissible limit. So you've got the time along the bottom in milliseconds and the permissible touch voltage up the left-hand side. These 4 levels on there, so you've got bare earth with bare feet, because obviously you've then got a very good connection between you and the general mass of earth. You've then got bare earth with somebody wearing standard shoes, and we're saying standard shoes shall have a footwear resistance of 4 kiloohms. Then you've got a little bit higher, because you've got 75 mil of chippings, then 150. So if you ever you see these substations, and you think, oh, look at that, it looks lovely, like a rock garden, bit of chippings on the ground, looks lovely. It's there for a reason. It's actually keeping you safe. And that high resistivity chipping on the ground, it's actually insulating you from the ground itself. So it's making things safety by design. Again, so it just shows you, again, going back to the store site again, touch voltages, they do vary across the site. Now, because we've got that very nice mesh in the ground there, and it's all the rebars all connected together, it's fantastic, that is. But as you come out, you can actually see towards the edge of the site, towards the edge of the earth system, you're actually, the touch potentials are starting to creep up. So that's something you have to be a little bit careful of. Step potentials, very much the same as touch potentials, but it's the potential difference between your feet. So you're only really interested in what's a metre and a half metre, something like that. So it's the difference in potential between your legs. And as I was sort of saying, if you inject a fault current into the ground just there, it will degrade or decay as it comes away from that point of injection. So because you've then got differences in potential across the ground, you will have differences in potential across your feet. So again, it's something you have to be very careful with. It's not cross his legs, up one leg, down the other. Luckily, it doesn't particularly go across the heart, but step potentials, again, that's it. The logic being, if you get the touch potentials right, the step potentials are usually right as well, because the permissibles for step are 7,000 volts, 8,000 volts for 1 second clearance time. So it's really quite high, as opposed to touch potentials, which can be a few hundred volts. Yeah, it is vital that the earth electrode system is installed as designed. Variance from the design can lead to the presence of dangerous touch and step potentials. The reason we say that is, it might be easy just to think, you know, guys on site was trying to knock the rod in the ground, and it's got a bit hard there. And you think, well, actually, I'm not going to put it down. I won't put it 4 meters down here, but it's nice and soft down there. Problem with that is, we've designed it, we've modelled that, so that earth rod there is usually, we put the earth rods at the corner of the earth electrode system, or the edge. And what we're trying to do there is, we're trying to drag that fault current that, that's sitting at the edge there, we're trying to drag it down deeper into the general mass of Earth, where it's not going to do any harm. If you start moving those rods around without actually asking the designer, you can alter all of these touch and step potential layouts. And so you can actually start causing yourself problems. Records should be taken of where conductor joints are and the resistance of each joint. Because damn me, you're going to have how many tons of soil over the top of these once it's covered up, and you're never going to get to them again. If you start getting a fault, or in years to come you start testing and you've got an open joint or an open resistance between one rod and another, then it's a good idea to know where these joints are, because at least you can dig at that point, and you know, 9 times out of 10 it could be the joint and not the copper itself. I think that's fairly self-explanatory. HSG 47 should be tested at all times. Right. Joints, although it doesn't stipulate a figure in the standards, it does sort of say, I think 50522 now does say about joints in earth resistant, in earth electrode system should be tested with a suitable meter or whatever. We tend to use these 10 amp micrometers, ductors, whatever. I mean, I've always used the DLR 010. There are other meters available, I'm sure, but that's cracking. Plump it on, auto ranging, does the job. You need to know that these joints are sound, and we are talking, you know, the joint should have a resistance that is similar to an unbroken length of copper. So if you've got a copper strip, a meter long, and it is 100 ohms, 100 microohms or something like that, and then you've got a joint in it, you need to make sure that joint is good enough so that is still 100-ish microohms. So you're actually looking across a joint somewhere in the region of 50 microohms, something along those lines. Because we are dealing with quite long duration faults, 1-3 seconds, it's not like lightning protection. Lightning protection is the part of our business where we've got clamps, you get the tapes, they're not quite sitting right, but if you clamp them down, there's that much energy coming from the sky that a bit of an air gap between the copper tape isn't going to cause you that many problems. And it's over within microseconds anyway. When you're dealing with 1-3 second clearance times, there's a lot of energy, a lot of heating, so you've got to make sure that joint is sound. What else have we got? Yeah, there you go, 50 micro, that shouldn't be microohms, that should be microohms, my apologies. A bolt to clamp joint should be in the region of 20 milliohms-ish, and they are-ish. System testing, 7430 actually stipulates person protective equipment introducing earth electrodes into an otherwise bonded earthing arrangement can result in high touch voltages. Consequently, appropriate insulated footwear, fire retardant clothing and insulated gloves 7.5 kV should be worn during testing. Now, that's as much as that says. It doesn't go into any great detail about that. But for me, if you have And again, I'm working on personal experience here. Big hospital in Nottingham, went to see their facilities guy, and he says, oh yeah, there were some guys came out, tested these earths the other week. I says, all right. I says, that's your HV network, that is. He says, how do you know? I says, because they're 2 meters apart from each other, and it's running right into that substation there, mate. You know. He says, oh, they've come along, they've disconnected them and put the earth rod, earth tester across them. He says, right. I said, I've got the clamp meter out of the car, put it round the earth cable. Yeah, 15 amps flowing through that. So, you know, it's things like that that people need to be a little bit more aware of. Disconnecting earths isn't the done thing anymore. There is technology out there, there is test equipment out there that, if designed correctly up front, you never ever need to disconnect an earth ever again. The way we do things is we put an earth rod in, we put a cable from the earth rod, the cable runs through the pit, that is then welded to the earth system. All you do then, pop the lid off the earth pit, you put the clamp meter around it, read the reading, done. That's it. No disconnection, no messing about, everybody's safe. So, I know I've flown through that, I know I've gone at 1,000 miles an hour. My apologies, I was 724. That's not bad going. At 1,000 miles an hour. Are there any questions?
How do you determine the percentage of earth fault that goes through the feeder cable?
It's down to cable type, cable impedance, whether it's trucks, whether it's 3-core, whether it's lead sheath, whether it's pill, whether it's steel wire armour. At the back of S34, this document, get your hands on, it's fantastic. It's a little light reading for the night time. There are tables and tables and tables of mutual impedances. At the back of there are formula for different configurations of earth systems. You can choose which formula fits your side, and you can just work through the calculations. Yes, you know, some of them are a bit more heavy than others. There are different methods of doing it. The old 60-40 split, that's what they always used to say, that 60% of the fault would go up the cable sheath, 40% would go down to earth. Is that right? Is it wrong? I don't know. Depends on what the configuration of the network is. I mean, we've had sites for IDNOs where they're on a long 11 kV run. I'm talking 5 kilometre 11 kV runs, and you've got 80% of the fault going to the general mass of earth because it's all clay and it's really, really good. So that's your lower impedance path rather than going up the cable sheet. So it's one of those that, unfortunately, it's not an easy, you shall do this each and every time. It does vary each and every job, each and every substation. It will be different. I can't give you a simple answer, sorry.
So we should commission soil resistivity tests. Should you specify? Especially as earthing seems to be very much CPD element. How can you design a B&C project if that information isn't provided?
We have seen some consultants starting to procure our services and our competitors' services, and actually getting the soil resistivity surveys done as part of the surveying package for a new building, for a new installation. They can then get us to do the design or whatever, and then at least you've got a design, much as you have for a lot of other systems in buildings. You have then got a design that you can then hand over to the contractor. The contractor can then price it and install it and work that way. That's one way of doing it. The normal way, I think, as everybody has done for another day, is leave it to the 11th hour and then panic about it at the end. Not the right way of doing it, though. I know exactly what you, yeah.
Not wanting to spark a debate between the consultants and contractors, but
sorry, well, just so you know, I'm Dave from Wallis, for the business manager. I'll comment at the end because it's a new presentation. I think the biggest issue with this is that because it's not spec'd and it's not, this is how it's done and this is how it should be done, because it is, I would say, an evolving part of